MS Ramaya University of Applied Sciences.
Hi students, let us discuss the measurement of the angle of a given workpiece using sine bar. This experiment aims at measurement of angles in a workpiece using a sine bar. A sine bar is an instrument used to measure angles in a workpiece. It consists of a hardened body, which is precision ground, and consists of two precision ground cylinders known as rollers at each of its ends. One of the rollers is enclosed in a square slot, while the other roller is not enclosed. The distance between the centers of the rollers is controlled, and the top of the sine bar is parallel to a line through the centers of the two cylinders. When the sine bar is placed over a level surface, the top edge will be parallel to that surface. Figure shows a typical sine bar and its parts. The distance between the two rollers of the sine bar are available in three ranges: 100 mm, 200 mm and 300 mm. The sine bar used in this experiment is of the range 200 mm. The sine bar works on the principle of sine angle. The sine of the angle AB having a length C in a right angle triangle having three sides, that is opposite side, adjacent side and hypotenuse side, which is BC, AC and AB as shown in figure, is given by sin theta is equal to BC by AB, which in this case is A by C. The sine of the angle in the component with respect to the experimental setup shown in figure is given by the equation sin theta is equal to H by L. The apparatus required for carrying out this experiment are a sine bar which has a center distance of 200 mm between its rollers, a slip gauge set, a height gauge, a Poppetus dial indicator, an angle plate, a surface table, the workpiece whose angle has to be measured. Here goes the procedure for carrying out this experiment. Initially, place the sine bar over the surface table. Position the workpiece over the body of the sine bar such that the side in the workpiece whose angle is to be measured on the workpiece is resting over the sine bar towards the side of the non-enclosed cylinder, and the edge being measured faces away from the cylinder. Use the angular plate as a support for the workpiece at the end of the sine bar so that the workpiece does not fall off the sine bar. The arrangement of the apparatus setup for carrying out the experiment is as shown in figure. If the angle plate is not placed as a support, the workpiece will fall off the sine bar when the roller is raised with the help of the slip gauges. Raise the sine bar towards the enclosed roller by ringing slip gauges and placing it under the enclosed roller such that the edge of the workpiece where the angle is being measured forms a straight line with its corresponding edge. Clamp a Poppetus dial on the vernier height gauge for measuring the straightness of the line formed by the edge of the component being measured with its corresponding edge. Move the height gauge such that the lever of the Poppetus dial runs over the straight line formed by the surface of the workpiece. The method of checking the straightness of the line formed by the edges of the workpiece using a Poppetus dial is as shown in figure. Note down the deviation observed on the dial indicator when the lever of the Poppetus dial runs across the surface of the workpiece being measured. The deviation should not be more than 0.02 mm, which is 20 microns. It is important to note that in an ideal scenario, there should be no deviation observed in the dial indicator. But there are some inherent variations in the environmental conditions where the measurement is being done, leading to small variations across the surface of the workpiece being measured. Hence, the tolerance of 20 microns has been given in this experiment. If the deviation observed in the dial is less than 20 microns, measure the height of the slip gauge combination rung together and note down this value as h. If the deviation is more than 20 microns, repeat the experiment until a deviation of less than 20 microns is obtained, and then measure the value h. The distance between the centers of the rollers on the sine bar is known to be 200 mm, which is depicted as L. Calculate the ratio of height of the slip gauge combination to the distance between the centers of the rollers, h by L. Use the sine principle and calculate the angle in the workpiece. If multiple angles are required to be measured in the same workpiece, repeat the same procedure using the h to be measured as a reference point. The readings obtained must be tabulated in the format of a tabular column. Carry out the calculations using the standard formula and find the angle in the workpiece. In case the workpiece whose angle is being measured is conical in shape, a sine center is used instead of a sine bar. It is similar to a sine bar only with the difference that it contains two pointed centers at its ends to mount the conical workpiece. This experiment does not need angular plate for supporting the workpiece. The rest of the procedure for measuring the angle in the conical workpiece remains the same as that followed in sine bar. The angle of the conical workpiece is measured by repeating the entire procedure. Figure shows a sine center along with the method of mounting the conical workpiece on the sine center. The methodology for the measurement of the conical angle follows the same procedure as in the case of sine bar. This experiment has some limitations. It is a tedious and a time-consuming process as compared to modern methods like measuring through a profile projector. Inaccurate results are an inherent part of this experiment, as variations are bound to be present in the environment where the measurement is being done. Inappropriate handling of the slip gauges may lead to scratches and dents on the ground surface of the slip gauges. This concludes the experiment measurement of the angle of a given workpiece using a sine bar.
Hello students, today we are going to conduct the experiment, the measurement of an angle of a given component using a sine bar or a sine center. The aim of this experiment is to measure the angle of a given specimen using a sine bar or a sine center. The apparatus used for carrying out this experiment is a sine bar. A sine bar is made up of hardened steel and it is chromium plated. It consists of two rollers at its ends. One roller consists of a square edge behind it and the other roller does not consist of the square edge. It has to be noted that the sine bar in itself cannot measure an angle of a component on its own. It needs help of slip gauges for measuring the angle of a workpiece. A workpiece, this is the workpiece whose angle has to be measured. We are going to measure this angle in this experiment. A sine center, this is a sine center which is similar to a sine bar This also consists of two rollers like a sine bar. The only difference is it also includes two between centers because the profile of the component which is being measured in the sine center is conical. Conical workpiece. This is a conical workpiece whose angle is going to be measured on the sine center. It consists of two centers in its ends. The angle which is being measured is this angle. A height gauge. This is a height gauge which is used to ensure the flatness of the edge surface of the workpiece when it is being measured. It consists of a base which is finely lapped, which ensures the flat seating of the height gauge on the surface table. A Puppetus dial. This is known as a Puppetus dial or a lever dial, and it consists of two clamps. We will make use of one clamp in this experiment to mount the Puppetus dial onto the height gauge. This Puppetus dial is used to check the flatness of the edge of the surface of the workpiece while carrying out the experiment. The height gauge clamp. This is the clamp which mounts the Puppetus dial onto the height gauge. As we had earlier seen in the height gauge experiment, this clamp was holding the scriber. In this experiment, this clamp will be holding the Puppetus dial. A standard slip gauge set or a gauge block set. This is a standard slip gauge set, also known as a standard gauge block set. It consists of 87 slip gauges and 2 wear blocks. The slip gauges are used in this experiment to tilt the sine bar at a given angle by mounting the slip gauges one upon the other over one side of the roller of the sine bar, and an angular plate. This is an angular plate, also called as an angular block. In this experiment, the purpose of this angular block is to provide support for the workpiece when the sidebar is tilted. Firstly, we will conduct the experiment measurement of an angle of a triangular workpiece using a sine bar. Let us start the experiment. Firstly, we will attach the Puppetus dial onto the height gauge. For attaching the Puppetus dial to the height gauge, firstly take out the clamp, loosen the screw such that the groove in the clamp gets widened. Now take the Puppetus dial and attach the groove of the clamp to the groove of the Puppetus dial and screw it tightly. Now we can see this clamp is attached onto the Puppetus dial. Now we have to attach this entire set to the height gauge. Take the height gauge clamp and fit it onto the height gauge. Now take the Puppetus dial assembled along with its clamp and insert it inside the gap of this clamp and tighten the height gauge clamping screw. There should be no play involved in the Puppetus dial. Next, we will take the sine bar and the triangular workpiece whose angle is to be measured. We want to measure this angle in the workpiece. Place the workpiece in this manner on the surface of the sine bar. As we have already said, a sine bar by itself alone cannot measure the angle of a given workpiece. It makes use of slip gauges to tilt the edge of the workpiece such that it becomes flat, and then by using the sine principle we will be able to measure the angle of the workpiece. It has to be noted that always the roller which contains the square edge has to be raised, and the roller which does not have any edge has to be placed on the surface table at all points of time. Now we will start raising one end of the sine bar using slip gauges such that this edge becomes completely flat. Now we will raise one end of the sine bar using slip gauges. Slip gauges have finely ground surfaces which are not supposed to be scratched. For that reason, we use two special blocks called as wear blocks. Before placing the slip gauge directly on the surface table, we need to keep these wear blocks on the surface table as a protection for the ground surfaces of the slip gauges. Before raising the sine bar on one end, place the angular plate on the edge of the sine bar so that it acts as a support for the workpiece and the workpiece does not fall off the surface of the sine bar. The sine bar works on the trigonometric principles of the sine angle. As we all know, sine theta is opposite by hypotenuse. In this experiment, when we raise this end of the sine bar, the slip gauges act as the opposite side and the sine bar will act as the hypotenuse side. Initially, we will start with the slip gauge 50 mm. Before you start the experiment, we need to wipe the ground surfaces of the slip gauge so that it is free of any dirt. The ground surfaces have to be wiped in one direction only. Place the wear block on the surface table. Place the 50 mm slip gauge on its ground surface upon the wear block. Place the second wear block over the slip gauge. Now place one end of the roller of the sine bar over the wear block. Use the angular block and support the sine bar. Now place the workpiece in supporting to the angular block. At this point of time, the opposite side, which is the height of the slip gauge, is measuring 54 mm, which comes from the 50 mm of the slip gauge and the 2 mm of both the wear blocks. Each of the wear blocks measure 2 mm, which makes it 4 mm. So the entire opposite side is measuring 54 mm. Now we need to check whether this edge is completely flat or not. This can be done by using the height gauge. The edge of the workpiece is said to be completely flat when the lever of the puppeteer's dial is run through on the edge and the puppeteer's dial does not show any deviation. The least count of this puppeteer's dial is 10 micron, which is 0.01 mm. So the surface is said to be completely flat if the variation in the puppeteer's dial is less than or equal to 30 microns, which is about 3 divisions on the dial. Slowly bring the tip of the lever of the puppeteer's dial in contact with the surface of the workpiece. Adjust the reading in the dial to 0 mm by turning the dial. It has to be noted that if the dial moves in clockwise direction, it means it is moving from a lower dimension to a higher dimension. If it moves in the anti-clockwise direction, it means it is moving from a higher dimension to a lower dimension. Slowly run the puppetus dial lever over the surface of the workpiece. You can see that the dial is already showing a deviation of up to 0.4 mm, which means it is lower in this area compared to this area. So the height of the slip gauge has to be raised further. Now remove the sine bar, take out the wear blocks and add another 4 mm onto the 50 mm slip gauge by using a process called ringing. Ringing is a process of attaching two ground surfaces of a slip gauge with each other using a twisting and a rotating force. Ringing is a process of attaching two slip gauges over its ground surfaces by using a sliding force as well as a twisting force. Now place the slip gauge combination measuring 54 mm over the wear block. Repeat the procedure as done earlier with 50 mm. You can observe that there is still a deviation of up to 0.1 mm, which means you need to further increase the height of the slip gauges for this edge to become flat. Now we have run three different slip gauges of dimension 50 mm, 3 mm and 1.25 mm, which makes the dimension 58.25 mm, including the 4 mm of the two wear blocks each. Similarly, we will test the flatness of this edge when the height is 58.25 mm. As you observed, there was literally no variation or maximum variation of up to 0.02 mm in the puppetus dial when the slip gauge measurement was 58.25 mm. So the opposite side in this case will measure 58.25 mm and the hypotenuse will be the length of the sine bar, which in this case is 200 mm. Using the formula sin theta equals opposite by hypotenuse, we can calculate the angle of theta, which is this angle. Now, similarly, we will be measuring the angle of the conical workpiece using a sine center. The basic procedure of carrying out the experiment is entirely the same as what was used in the sine bar. The only difference is in the mounting of the workpiece. Now we will see how to mount the workpiece onto the sine center. Loosen one side of the between center using the screw and mount the workpiece between the centers using the two centers provided on the workpiece. Once the workpiece is seating between the two centers, tighten the screw and start the experiment. The angle measurement procedure of the conical workpiece is the same as how it was carried out in the sine bar experiment, which means we will be raising this end of the sine center using slip gauges and checking the flatness of this edge. Similarly, use the sine theta equals opposite by hypotenuse formula, where again the hypotenuse will measure 200 mm and opposite side will be the length of the slip gauges at the point in which this edge will be completely flat. This concludes the experiment, measurement of the angle of a workpiece using sine bar and sine center.
At MSR UAS, we spark your imagination unlike any other.